Vectors. All motions we have been considering are rectilinear, that is, along a straight line. Now we must go one step farther. We gain an understanding of the laws of nature by analyzing the simplest cases and by leaving out of our first attempts all intricate complications. A straight line is simpler than a curve. It is, however, impossible to be satisfied with an understanding of rectilinear motion alone. The motions of the moon, the earth, and the planets, just those to which the principle of mechanics have been applied with such brilliant success, are motion along curved paths. Passing from rectilinear motion to motion along a curved path brings new difficulties. We must have the courage to overcome them if we wish to understand the principle of classical mechanics, which gave us the first clues and so formed the starting point of the development of science. Let us consider another idealized experiment, in which a perfect sphere rolls uniformly on a smooth table. We know that if the sphere is given a push, that is, if an external force is applied, the velocity will be changed. Now suppose that the direction of blow is not, as in the example of the cart, in the line of motion, but in a quite different direction, say, perpendicular to that line. What happens to the sphere? Three stages of the motion can be distinguished: the initial motion, the action of the force, and the final motion after the force has ceased to act. According to the law of inertia, the velocities before and after the action of the force are both perfectly uniform. But there is difference between uniform motion before and after the action of the force. The direction is changed. The initial path of the sphere and direction of the force are perpendicular to each other. The final motion will be along neither of these two lines, but somewhere between them, nearer the direction of the force if the blow is hard one, and the initial velocity small, nearer the original line of motion if blow is gentle and initial velocity great. Our new conclusion based on the law of inertia is, in general, the action of an external force changes not only the speed but also the direction of the motion. An understanding of this fact prepares us for the generalizing introduced into physics by the concept of vectors. We can continue to use our straightforward method of reasoning. The starting point is again Galileo's law of inertia. We are still far from exhausting the consequences of this valuable clue to the puzzle of motion. Let us consider two spheres moving in different directions on a smooth table. So as to have a definite picture, we may assume the two directions perpendicular to each other. Since there are no external forces acting, the motions are perfectly uniform. Suppose further that the speeds are equal, that is, both cover the same distance in the same interval of time. But is it correct to say that two spheres have the same velocity? The answer can be yes or no. If the speedometers of two cars both show 40 miles per hour, it is usually to say that they have the same speed or velocity, no matter in which direction they are traveling. But science must create its own language, its own concepts, for its own use. Scientific concepts often begin with those used in ordinary language for the affairs of everyday life, but they develop quite differently. They are transformed and lose the ambiguity associated with them in ordinary language, gaining in recurrence so that they may be applied to scientific thought. From the physicist's point of view, it is advantageous to say that the velocities of two spheres moving in different directions are different. Although purely a matter of convention, it is more convenient to say that four cars traveling away from the same traffic roundabout on different roads do not have the same velocity even though the speeds as registered on the speedometers are all 40 miles per hour. This differentiation between speed and velocity illustrates how physics, starting with a concept used in everyday life, changes it in a way which proves fruitful in the further development of science. If a length is measured, the result is expressed as a number of units. The length of a stick may be 3 feet 7 inches. The weight of some object, 2 pounds, 3 ounces, a measured time interval so many minutes or seconds. In each of these cases, the result of the measurement is expressed by a number. A number alone is, however, insufficient for describing some physical concepts. The recognition of this fact marked a distinct advance in scientific investigation. A direction as well as a number is essential for the characterization of a velocity. For example, such a quantity possessing both magnitude and direction is called a vector. A suitable symbol for it is an arrow. Velocity may be represented by an arrow, or briefly speaking, by a vector whose length in some chosen scale of units is a measure of the speed and whose direction is that of the motion. If four cars diverge with equal speed from a traffic roundabout, their velocities can be represented by four vectors of the same length. In this scale used, 1 inch stands for 40 miles per hour. In this way, any velocity may be denoted by a vector, and conversely, if this scale is known, one may ascertain the velocity from such a vector diagram. If two cars pass each other on the highway and their speedometers both show 40 miles per hour, we characterize their velocities by two different vectors with arrows pointing in opposite direction. So also the arrows indicating up-down and downtown. Subway trains in New York must point in opposite directions, but all trains moving up-down at different stations or on different avenues with the same speed have the same velocity, which may be represented by a single vector. There is nothing about a vector to indicate which station the train passes or on which of the many parallel tracks it is running. In other words, according to the accepted convention, may be regarded as equal. They lie along the same or parallel lines, are of equal length, and finally have arrows pointing in the same direction. Since the starting point doesn't matter, these vectors can be represent the velocities of four cars moving away from the same traffic roundabout, or the velocities of four cars in different parts of the country traveling with the indicated speed in the indicated directions. This vector representation may now be used to describe the facts previously discussed concerning rectilinear motion. We talked of a cart moving uniformly in a straight line and receiving a push in the direction of its motion, which increases its velocity. Graphically, this may be represented by two vectors, a shorter one denoting the velocity before the push and a longer one in the same direction denoting velocity after the push. The meaning of the dotted vector is clear. It represents the change in velocity for which, as we know, the push is responsible. For the case where force is directed against the motion, where the motion is slowed down, it is clear that not only velocities themselves, but also their changes are vector. But every change in velocity is due to action of an external force. Thus, the force must also be represented by a vector. In order to characterize a force, it is not sufficient to state how hard we push the cart. We must also say in which direction we push. The force, like the velocity or its change, must be represented by a vector and not only by a number alone. Therefore, the external force is also a vector and must have the same direction as the change in velocity. In the two drawings, the dotted vectors show the direction of the force as truly as they indicate the change in velocity. Here the skeptic may remark that he sees no advantage in the introduction of vectors. All that has been accomplished is the translation of previously recognized facts into an unfamiliar and complicated language. At this stage, it would indeed be difficult to convince him that he is wrong. For the moment he is in fact right, but we shall see that just this strange language leads to an important generalization in which vectors appear to be essential.